Welcome to EE533's final video demonstration. Uh, let's get started. Meet Muriel. She lives all alone, far away from the town. She looks kind of sad, right? Well, let's find out why. Day to day, she faces problems like pests inside her house, proven like when she is presently sleeping. Mr. Ski Mask might threaten her safety. Good thing she kept her windows locked that day. Just another day, she was having a small get together with her friends. They were just chatting, and she saw her friend Victoria put down. Victoria was like, "Hey, Muriel, I'm in serious trouble. Look at my phone. It's locked, and some hacker is threatening me to, they're demanding me for Bitcoin, and if I don't give them, they're gonna delete all my data. I don't know what to do." Muriel is all confused. Another day, a similar thing happened, and she was talking to her sister. Her sister told Muriel, I was just another day I was trying to place an order on Amazon. I went through a website, I entered my details, and all of a sudden, a few minutes after, got an email and somebody placed a huge order. You can see the spoof website. Happens to the best of us. Muriel's all confused. Is there anything out there for her to protect her from all these things happening to her? Well, things are really serious than what we saw in Muriel's life. Companies like DarkSide, this chemical distribution company, they all get affected by ransomware, and the hackers demand tons of money, and when there's no way out, they end up paying, and it's a huge revenue loss for a lot of companies. There's one case like where there was estimated damage of 38 billion because of one worm. This is another worm happened in 2008. Facts are like 1 out of 3 homes are actually affected with malicious software, and in a study, like 270 corporations over a year were 31% of the attacks were increased, and every year it keeps on increasing, and almost like 47% of American adults had their personal info leaked. Sounds pretty serious. Well, everyone has heard of firewalls, right? It does a job. Like we have well, most of the people have it installed in their laptops, and it does packet inspection, but not so thoroughly. It's kind of like analogy if I put a repairman comes to your house, and you allow him to enter, but just on the face value, what if he's carrying a gun inside her vest? And that's trouble. They're prone to DDoS attacks, so similar to a analogy, a gang of robbers, it's pretty hard for even a huge task force to stop them. So firewall has its own set of problems. Shallow packet inspection, exposed to DDoS attacks, no anomaly detection, it's limited to layer 4. Well, there are solutions. Traditional intrusion detection systems like SNORT, PSNs, Suricata, they're all there. Software-based approaches, but then they can do deep packet inspection. They are good enough against distributed denial of service attacks. You can do anomaly detection, have custom rules so that you can set up your own rules. That's a good thing for corporation. So it seems like a better choice than a firewall. But there's a huge problem with these two. It against high bandwidth DDoS attacks, they are really inadequate. And another pain area is they're really expensive to implement if you are targeting a certain higher bandwidth. That's where our product comes in. Thanos, a true hardware accelerated network intrusion detection system operating system. It protects against all signature-based attacks, has lower capital costs for same throughput, and even lower operational costs for zero false positives. All these three features make Thanos a really a better ideas uh, than what the market has to offer. So usually our product Thanos sits inside a router and just monitors the traffic coming through it. It is just a dual core multi-thread processor, but there's more to it. It has a dedicated hardware accelerator. It does the job and removes the software overhead caused by traditional ideas like SNOT. So it does our CPU. It does the header reconstruction according to the SNOT rules, feeds it to the IDS accelerator. Then in IDS accelerator, we have a bunch of cams, and all the fields go to the cams, and we have already hard coded so that it generates index and it goes to Bloom filter, which is a probabilistic data structure which we're implementing.
So once we extract the headers and generate the index, we will be concatenating the index to n bytes from the payloads. We'll be looping from the beginning to the end of the payloads. And these combinations are passed into our Bloom filter, which consists of multiple hash functions and the hash table. So how this works is that the combination will be put in hash functions that generates index, and we'll be checking on in the hash table if these indexes are ones. So the PID file pattern is actually a snort rule which detects and attempts to change the PID file of one of the servers, which synchronize many important processes such as financial transactions. So once IDS detects this pattern or these patterns, it will put on a label and then pass it back to the cores. However, because Bloom filter could possibly have false positive, we will do a secondary verification on software. So we'll be passing um, our labeled packet to the secondary verification software node, including the extracted headers for efficient matching. This is the whole process of processing one packet, including header field extraction, index generation, DPI, packet redirection if needed. So when the second packet comes, the second core can actually start computing the header extraction of that packet. In this case, we can achieve higher throughputs and hide the overhead of the header extraction.
Hi. So we will now discuss what is the current state of affairs as we submit this demo. So we have currently implemented 8 rules. However, the careful consideration which has gone into deciding the architecture makes our design scalable up to 11,500 rules. What is the category of rules? So basically, we are saying that uh, all the rules which are inside SNOT version 2.9, which have a single content field, uh, can actually be irrespective of whether it is 7 bytes or 3 bytes or 115 bytes, uh, can be actually filtered out by our design. Currently, the demo which we are presenting to you has a pattern of 7 bytes available, and it has a capability uh, to decode TCP and UDP traffic. Of course, TCP includes HTTPS. And on the right hand side, you can see that, like as my colleague explained, that we are currently filtering out rules based on protocol, IP addresses, port number, and the content field. and the basic action which we are taking right now is drop. I will move on. So this slide shows the the real demonstration which my friend presented a few minutes earlier. Here we can see that uh, although our uh, although our bandwidth is wobbling, but we can see a stable pattern of somewhere between 2 Gbps and 2.5 Gbps, whereas for SNOT it hovers around 150 Mbps only. So we have around a 10x to 11x advantage in terms of bandwidth as compared to SNOT, which is implemented as as a pure play software solution. I will now take this opportunity to present the business case. So, for example, we showed that we have an advantage in terms of bandwidth. So, when we calculate the bandwidth of our design, and we instead of calculating it over NetFPGA 1G, we take these numbers and uh, and try to simulate what can be the results if we have a more powerful NetFPGA, which is NetFPGA Sume. We see that the bandwidth is lying somewhere between 25 Gbps. So we try to search for similar devices which are available in the market. Cisco, which is one of the leading players, has got a IPS throughput of 21G from a device called 3120. This 3120 uh, can support 21 Gbps of bandwidth, and the list price is somewhere around 30,000 USD. Therefore, we see that for for this 21 Gbps bandwidth offered by a Cisco Firepower 3120, whereas if we try just to try to amplify a design and import it into NetFPGA Sume, we are around 22 Gbps. So we are roughly around similar bandwidth. However, if we see the board price of Sume versus the Firepower price, there is a 5.5x cost advantage. Cost means that the cost which is the cost which will be offered to you, not the price which will be offered to the end consumer. So in terms of pure play cost, we have an advantage of 5.5x. Moving on, um, here we just show you now the numbers. So we have already discussed the bandwidth advantage which we have and the cost advantage which we have. But is it a is it a large market which can be served? So we see that these are the numbers from IDC for quarter 2 2022, and we see that the quarterly revenue of this market is around 6 billion. Mind you, this 6 billion is the security appliance market only. I'm not discussing the overall security market. I'm only discussing security appliance market, where Cisco Firepower is a series, is an offering from Cisco for security, which offers IPS, IDS, etc. as in production. Okay, so 24 billion of market, and what are the margins currently? So Cisco, which is a public listed company, has a after tax margin of 20%. 20% after tax margin is a really healthy or so-called fat margin in this business. So we have seen that we have advantage in terms of bandwidth. Our costs are low. There is a big market, and players are currently earning a fat margin, which means that let's assume that we also have a similar margin. Therefore, that 5.5x cost advantage now translates into a 3x price advantage for end consumers. So end consumers, if they want to have a 21 GB, if they have a requirement of 20 Gbps device which can do IPS or IDS, they can actually buy a Cisco Firepower versus our device, which will be costing them roughly around 2k around 20k dollars, whereas Cisco Firepower will be costing them 6k dollars. So 2k 2000 USD versus 6000 USD is what we are offering to end consumers. So there is an advantage not only in terms of, so end consumers are benefited by having 3x, by having to pay 3x lesser cost for similar bandwidth. Just simulating these numbers, we find by taking the overall market size, dividing it by the average selling price of in the market, we find that there are roughly 6.1 million devices, security appliances sold each year. And if we just multiply it by some back of the envelope calculations, 20% margin, we believe that we have a potential to reach a 20% market share in 3 years, which translates to roughly 1.67 percentage incremental market share per quarter. So only for the first quarter itself, we can have a profit projection of 43 million USD. Moving on. So this 43 million USD first quarter, if it keeps on increasing at the rate of 1.67%, which means that by end of 3 years we will be somewhere around 15-16% market share, which by the way is also the market share of the leading players. So we are not saying that we are trying to have 50% market share. We are saying that whatever the market share which existing players have, if also we also try to have just a similar market share, we are looking at a 3 billion quarterly revenue. Lastly, just for the techies in you, we would just want to show that we have a very stable toolchain available. So, for example, this slide presents you the logic analyzer, which is a home built, home custom brewed logic analyzer, which shows the state of the entire design across various parameters, uh, which are segregated. Similarly, we also had a when we were designing the compiler, we did not design the compiler only to generate a file which has to be consumed by the memory, but we also generated a design which can be decomposed and can be understood by humans. So therefore, all we what we want to show is that we have a very elaborate and stable toolchain available. To sum up, we have a 5.5x cost advantage, which is for us, a 3x advantage for end consumers, 20% net margin to the players, 24 billion the yearly market size, and a real live demo as shown by my team. Thank you.
Of the code. Let's begin with our worm squasher. So we have installed our worm squasher in the IDS. We have two instances for the worm squasher for the dual issue part. These are various signals which are going from the CPU to the worm squasher. Our worm squasher is basically the hardware accelerator. Let's dive deep into the worm squasher now. This is our worm squasher over here. We have some internal signals over here going on. We have a header police, which is basically the header inspection. We have a couple of bloom sets which are composed of some hash functions and the associated bloom filter. So we have around 10 bloom set for a total of 10 display windows from the CPU, and we have a simple state machine so that the CPU cores can alternate between the various hardware accelerator available to it. Okay, let's dive deep into the bloom set now. Bloom set is composed of some bloom filter and hash functions. So according to the calculation that we did for achieving 0.01% of false positive accuracy, we got a total of 9 hash functions, and in order to create those 9 hash functions, we used the seed to generate different hash function values. All these values are fed to the bloom filter, and we correspondingly get a match. Okay, let's just check the hash generator. This is our hash generator. So our hash generator works on the following principle. So we have a D vector, which is a vector consisting of some random values which are basically dependent on the total length of our bit array. In our case, the bit array is of 115 bits. The closest power of 2 is 128. So therefore our D vector will be having 128 bit D elements, and depth of the D vector will be equivalent to the input bit. So our input bit size is around 59 bits. That's why our D vector's dimension will be 159. Now our hash function is calculated according to the XOR dot product between D and I, which basically means each element of the D vector will be ANDed with each bit of the input data, and after adding each element with each bit, we will be XORing everything. At the end, we are also XORing it with the seed in order to produce a different hash output, and also we are modding it with 115 so that the output only remains between 0 and 115. This is how our hash is generated. Let's go to the Bloom filter, where we have actually stored our Bloom array. Over here, simply we are accessing the Bloom array using the hash values as the address to the Bloom array, and the match condition for this Bloom array will be when all the bits of the hash function address will be 1. Let's talk about the header police or the header inspection part. So we are basically giving the input IP, the output IP, protocol, input port, and the output port. We have created a simple case statement where for each and every combination of input output IP or input output port or protocol, we are assigning some index value to it. For example, for this particular combination, which is home to external, we are attaching this bit 0. For external to home, we are attaching this bit 1. MSB for every match register represents the match condition. So if the MSB is 1, we have a match, and if it is 0, we don't have a match. This is done for every other header field, and finally we have a final match, which is basically produced by ANDing every MSBs of the match buffers, and the index is basically generated by concatenating the remaining bits. So this is the overall architecture of our worm squasher, and as you have seen in the demo video, it works pretty well. So my name is Harsh, and I'm going to show you how we configured SNORT, what rules did we apply, and how we measured the bandwidth for the SNORT system. So over here I'll show you the SNORT configuration file by using this alias. As you can see, I'll just search for 2.9, and we see over here we have included a rule file called rules v2_9_7bytes.rules. Now we also configured the home and external net. So our home net is 10.1.0.3 and external net is 10.1.1.3. Now going back to our SNORT rules, which we can access using this alias, we have around 8 SNORT rules. These are the SNORT rules, and as you can see, like all the SNORT rules are having the traffic flow from external net to the home net. You can analyze the SNORT rules further, but I'll just close it for now. Okay, now we will first source our SNORT, source the rules of our SNORT using this alias. Now our SNORT is ready to be run. We run our SNORT using this alias, and now our SNORT is running. Let's start a server on our node 0. For that, I'll use netcat with port 123, and I'll create a client over here which will send our data. Now our data 4.txt has a pattern along with some data. Let's see what bandwidth we get. Okay, so currently as we can see, we are getting no response from the client. We can assume that our snort is working fine and it is dropping the packet which is malicious. Let's close the client over here and look at the statistics for the server. We again send the data to the same server. Here we can see our client sent the data successfully to the server, and we are getting a bandwidth measurement over here which is around 169 megabits per second. Let's run some other data through for the same server and let's check what bandwidth we are getting for them. For example, we send data 1 to the server. Oh sorry, I'll have to restart the server for that. Okay, let's wait for the transaction to complete. We are getting around 170 megabits per second over here again. Let's again try with data 2. Again around 170 megabits per second. Okay, so we can conclude that our bandwidth for the software snort is around 170 megabits per second. Create these snort on our hardware using Hardware Accelerator, and we will be measuring the bandwidth as well as detecting that a malicious packet will be dropped. So first let's kill all the RISC-V processes and download our file. So this is done, and again run the RISC-V process. Let's create a server over here and start measuring. Okay, going back over here, let's send some data. As you can see, we are getting around 2.05 gigabits per second. Let's run a couple of more tests. 1.31 gigabit, 1.15, 1.87, 2.18 gigabits per second. So we can say our network processor is running at roughly 2 gigabit per second. Okay, after couple analysis, like we can also assume, because right now we are running on a single port, but after, if the processor is running on all the ports available on the NetFPGA, then it can achieve up to 2.5 gigabits per second. Okay, now let's test how our packet will be dropped for a malicious packet. Okay, so let's analyze a Python. So we created a Python script where we'll be sending a malicious packet. Okay, so I'm opening the Python file over here, which is the malicious UDP. Okay, so over here we have a message which contains PID file. This PID file is a content which is a part of a rule. Now let's send this content to our server. Before sending it to our server, let's create a server over here. So Python env udp server. Oops, we have to kill the server first. Okay, I need to check the history before killing it. So okay, we need to know the process ID of the Python server, which over here is 4587. So let's kill it first, and now again turn the server back on. Okay, so before sending a malicious packet, let's send some benign packet. Over here I'll just show how a benign packet looks like. So this is our benign packet, which is some gibberish over here. Let's try sending it first. So by using our Python compiler, we send a benign packet which we are receiving successfully. Now let's try sending a malicious packet. And as we can see, okay, so this is not a malicious packet actually. This is another benign packet which is successfully received. Sorry about the file name, but the malicious packet that we just observed is not received by the receiver, and it is successfully dropped. So our network processor is successfully dropping the packet. Like the software SNORT.